So, well, the detail I didn't mention, I'm not using, the subset 1 and 2 are used to train the system, 2, 3, and 4 to classify. But I'm not using the phase for classification to training, so they are independent. Subset 3 is a little bit more difficult, so it goes more or less here, with 17 or so. In the subset 4, we reached 90–70%, which is, we do need all the subregions of the phase. So if we compare this to the state-of-the-art methods, TPC is gonna be here. These are generic methods, meaning just take correlation. You can take correlation of any kind of image, right? Eigenphase and cones attached. This starts to be more specific to phase, and these are really phase recognition methods. Meaning, TPC is generic. We can use it for whatever, not only for phase. And we have very, very high results. So it's very comparable to what we have in state-of-the-art methods. So now we want to apply TPC to another completely different kind of task. We want to know if, let's say we have pictures of different regions of this room. We get these pictures, and we want to know if somehow extracting the TPCs of those images, we could have a notion of distance between different points. So just to clarify, we got a region, a square region like that, and we take pictures in each of these positions with distance of 35 centimeters each, and we made the panorama view in the 4 different directions, okay? 0, 45, 90 degrees. So for each of these regions, I will show examples so it gets clear later on. We got all these pictures and we composed a panoramic view on each of these positions. This resembles more or less the way a rat would see. No, we have like almost the 270, 290, almost the whole panoramic view. So this is the pictures we did inside of the lab. So this is myself. So these pictures were done. Imagine this first picture we did here over all the orientations, the direction, and we composed this and made a panoramic view of this picture. So we did this. You can see for all these different points here, we're going to have this kind of plots, right? So with this picture, using the same salience map, we extracted 20 salient points on each of these images. We took the TPC and we compared among themselves. We took the correlation. So what we can show, given a certain point, let's say we are in a certain point here, we have the correlation to its neighbor, let's say TPC, would be of 0.4 or less with this variance, and would decrease as we go further or far from this point. It means with this plot, we can have a notion of distance with TPC, meaning the TPC code can give us a hint where we are. Cesar, with his model, with his hippocampus model, he could generate place cells out of that. It was the other work he did. So it just pretty exactly the same model we use for face. Just get this model, we get this representation. So it's very generic in this sense. We don't need to rewire the system. So the conclusions that the robust is encoding in generic, as we have shown. So for character recognition, for shapes, synthetic shapes, as it's published in 2004. for faces and for representing position, to give a notion of position inside of the environment. So the wavelet readout system is a good strategy, which makes the temporal code much smaller, reduce this in a factor of 8. It's like a compressor system, which gets only the core information. And this for me is a highlight, because TPC, being generic, performs as good as the best face recognition methods we have in the literature. Just we refer with this paper of people in Yale. Okay, that's all. Thank you.